Chapter 4 Entropy. Section 4.1 Definitions of Entropy. In statistical thermodynamics, Boltzmann proposed an equation for entropy. Entropy equals the Boltzmann constant times the natural logarithm of W. W is the number of microstates accessible to the system, and the Boltzmann constant K sub B is equal to the ideal gas constant divided by the Avogadro constant. K sub B is 1.38 times 10 to the power of negative 23 joule per Kelvin. If we have n particles occupying various energy levels, we can compute the number of microstates accessible to the system. This uppercase W is n factorial divided by a1 factorial, a2 factorial, a3 factorial, etc. This n again is the total number of particles. A1 is the number of particles in energy level 1. A2 is the number of particles in energy level 2. A sub I is the occupation number of energy level I. In this diagram, as heat flows into the system, the number of microstates changes, going from 5 to 10 to 30. So over here, we have 5 particles, so 5 factorial on top. And then we have 4 particles in energy level 1, 1 particle in energy level 2, therefore W is 5. Over here, when heat flows into the system, one of the 4 particles can move to the second energy level. Now we have occupation numbers 3 and 2. W is 5 factorial over 3 factorial and 2 factorial, we get 10. If heat keeps flowing to the system, now we have a particle in the second lowest energy level. In this case, W is 30. When there's no particles in an energy level, we have 0 factorial, and 0 factorial is equal to 1. Again, in statistical thermodynamics, we have an equation for entropy proposed by Boltzmann. Entropy is equal to the Boltzmann constant times the natural logarithm of W, and W is the number of microstates accessible to the system. So the system can be in any one of the W microstates. In thermodynamics, however, we have a different definition for entropy, and it's defined indirectly. We define the differential of entropy. ds is equal to dq reversible over t. So over here we have to have a reversible process, and then we can measure the amount of heat that flows into the system at a constant temperature T. That way we get the expression of entropy. Later in statistical thermodynamics, we can prove these two definitions are consistent with each other, and therefore we have the exact differential of entropy is equal to d, the exact differential of Kb, times the natural logarithm of the number of microstates. It's also equal to dq reversible over a temperature T. And we can equate these two sides. And over here we have kBT times the exact differential of L and W is equal to dq reversible. We can now integrate both sides at constant temperature. Then we have this q reversible is kBT times the difference between the logarithm of final W minus the logarithm of initial W. And in the end, we have this equation. Okay, the final number of microstates divided by the initial number of microstates is a exponential function. It's e to the power of q reversible over kBT. So if q reversible is positive, we have more microstates in the end. If q reversible is negative, we have less microstates in the end. The number of microstates accessible to a thermodynamic system increases as heat flows into the system in a reversible isothermal process indicated by this equation. And loosely speaking, heat increases the disorder and thereby the entropy of the system, while work does not, because when we do work to the system, we're not changing the occupation numbers. Entropy is a state function the change of entropy depends only on the initial and final states of the system. Therefore, the cyclic integral of ds must be 0, so it's expressed here. By the simplicity of this equation, the exact differential of entropy is equal to dq reversible over T. This equation can hardly be used to calculate the entropy change directly, because there's no simple relation between this temperature T and this dq reversible, and it's often more convenient actually to use this equation to rewrite the equation for ds, because du is dq plus dw. We have du is equal to dq reversible plus dw reversible for reversible processes. Again, du is equal to dq plus dw for all processes. Therefore, we can use that equation for reversible processes. Therefore, ds is equal to dq reversible over T, and dq reversible is du minus dw reversible. And dw reversible is simply negative pdv. And therefore, we can have this ds is equal to du plus pdv divided by T. Now, the internal energy can be expressed as a function of temperature and volume. Therefore, du can be expressed in terms of dt and dv. It's delta u over delta t times dt and plus delta u over delta v times dv. Now let's examine this part. Delta u over delta t under constant volume condition is simply the isochloric heat capacity. Why is that? Under constant volume condition, work is 0, and delta u is just delta q under the constant volume condition. So over here we see delta q over delta t under constant volume condition. Isn't that just C sub V, the isochloric heat capacity? And over here, delta U over delta V on a constant temperature condition is T times delta P over delta T on a constant volume condition minus P. We can prove this expression of delta U over delta V in chapter 5 after we learn the Maxwell relations. So for now, we'll just use this. And now we can plug in the expression of du. Well, it contains 1, 2, 3 terms. We will replace this du with these 3 terms. So ds is equal to du plus pdv over T, and then we plug in this 3 terms for du. Fortunately, this pdv and this pdv cancel, and then we have, in the end, only 2 terms. The exact differential of entropy is Cv times dt over T plus delta P over delta T times dV. So it comes from here. This is delta P over delta T on a constant volume condition times dV. What about the temperature here? T and T cancel, and this negative pdV and positive pdV cancel. Now we have this expression. And because entropy is state function, so somehow if both the temperature and volume change for a system, we can always allow the temperature change first and followed by the volume change. Therefore, the finite change of this entropy is the integral of Cv dt over T and the integral of delta P over delta T on a constant volume condition and dV. Somehow we can evaluate this delta P over delta T on a constant volume condition for an ideal gas. It's very simple. It's just P over T or nR over V. We can evaluate this for Van der Waals equation, and the math is more complicated, but approximately this is also nR over V. For solids and liquids, actually delta P over delta T on a constant volume condition can be expressed as alpha over kappa, and alpha and kappa are approximately constants for liquids and solids within a moderate temperature range and pressure range. We just need to plug in the values of alpha over beta here, and then multiply it by the change of volume. We get the second component. So that's not too bad. And usually we will be given the molar heat capacity for the substance, and then multiplied by N, we get C sub V. Now, it's possible to express ds in terms of dt and dp as well. Remember, among pressure, temperature, and volume, there are only 2 independent variables. Which 2? Well, we just choose the 2 variables that make our derivation more convenient. Now let's look at this situation. What if we want to express entropy in terms of temperature and pressure? For example, in some cases, both the initial and final temperatures and pressure are given, and we would like to compute entropy this way. And then ds is dq reversible over t, and dq reversible is du minus dw reversible. dw reversible is negative pdv. Now we have this equation. And remember, u is h minus pv based on the definition of enthalpy. Enthalpy is u plus pv. So now we have on the top dh minus dpv plus pdv. We can expand this. This is pdv plus vdp based on the product rule in calculus. Now we have this equation. It's dH minus VdP over temperature. Now we will express enthalpy in terms of temperature and pressure. dH is delta H over delta T times dt plus delta H over delta P times dP. Pay attention to the two subscripts. And now if you look at this one, delta H over delta T under constant pressure condition is simply Cp. And then delta H over delta P under constant temperature condition is volume minus T times delta V over delta T. We can prove this derivation for delta H over delta P is this in chapter 5. So now we're going to plug in the expression of dH. So 1, 2, 3, three terms on top for dH and then minus VdP. And then fortunately this VdP and this negative VdP cancel. So we have only two terms left for the differential of entropy. The two terms are Cp dt over T and also negative delta V over delta T times dP. And again, entropy is a state function. So if both temperature and pressure of the system change, we can allow the temperature change first to calculate the entropy change. And then we allow the pressure to change. The entropy of this system can then be calculated using this equation. The finite change of entropy delta S is the integral of Cp times dt over T and then minus the integral of delta V over delta T times dP. So we have only two terms in this expression of the finite change of entropy. So note that this ds can be expressed in terms of dt and dp or in terms of dt and dv. And again, because there are only two independent variables out of PVT, it's okay to pick any two variables. You can even express entropy as a function of PV, but it's not very convenient. So usually we say the entropy is a function of TP or a function of TV. And we got these two expressions for ds. ds is Cv dt over T plus delta P over delta T times dV. ds is equal to Cp dt over T minus delta V over delta T times dP. Which equation should we use? Well, just use the one more convenient for us. For example, if we are given the initial temperature, volume, and the final temperature and volume, I would use the equation on the left. If we are given the initial and final temperature and pressure, we will use the equation on the right. Now, the differential of entropy may be expressed in terms of dt and dp or in terms of dt and dv. So we have these two equations over here, and therefore these two equations should be exactly the same. The reason is entropy is a state function, so there's only one way to calculate the difference of entropy. Given the same, there's only one possible value of delta S between the initial and final state, and therefore this expression should be equal to this expression. So we write that equation here: Cv dt over T plus delta P over delta T times dV is equal to Cp dt over T minus delta V over delta T times dP. And now we move this dt term to one side and the dV dP term on the other side. We have this equation. And now we see Cp minus Cv times dt over T is equal to the sum of two terms. One is delta P over delta T times dV, one is delta V over delta T times dP. We can further expand dV because V is a function of temperature and pressure. dV is delta V over delta T times dt plus delta V over delta P times dP. So now we actually make this expression more complicated. Now we have three terms. The first term is this times this, we put it here, and then delta P over delta T times delta V over delta P over here, and then we have a third term here. By looking at these three terms, we notice this one depends on dt, this one, well, it depends on dp, this one depends on dp, and somehow these two terms cancel, and why the third term and the second term cancel? Well, we will use the reciprocal rule and the triple product rule in calculus. This delta P over delta T times delta V times over delta P, and then times delta T over delta V is -1. Therefore, the product of these two is -1 over delta T over delta V. Using the reciprocal rule, we can flip this, and then we have negative delta V over delta T. Look at this. This is negative delta V over delta T. This is positive delta V over delta T. And they have the same subscripts. Therefore, these two terms cancel. We have only one term left, and dt cancel. We will get a expression for Cp minus Cv. So we have this expression. Again, we're going to cancel dt and dt. Both sides multiplied by temperature. We have the expression for Cp minus Cv. It's temperature times delta P over delta T times delta V over delta T. Over here we have volume in the subscript. Over here we have pressure in the subscript. So again, this is the analytical expression for Cp minus Cv for all substances, regardless of the state, whether it's a gas, a liquid, a solid. We can always use this equation. And in summary of this section, the exact differential of entropy can be expressed in various ways. We usually use these two equations. In the first equation, entropy is expressed as a function of temperature and volume. In this equation, entropy is a function of temperature and pressure. When do we use this equation or this equation? Depending on the information given to us. If we know the temperature and volume, we use the first equation. If we know the temperature and pressure, we use the second equation. Again, these two equations hold for all substances, regardless of the state, whether it's solid, liquid, or gas. And also, by equating these two equations, we can actually derive the expression for Cp minus Cv. It's temperature times delta P over delta T under constant volume condition, and then times delta V over delta T under constant pressure condition. Cpm minus Cvm is simply T times delta P over delta T, and then over here we need to divide this volume by the number of moles. So we have delta Vm over delta T under constant pressure condition.